Okay, so remember that a coefficient and a subscript are two different things. So we're going to circle the subscripts. Okay, subscripts can be found after the chemical formula. So if we see a number after the element, it will apply to that element. A coefficient means that it is in front. Okay, just like in math, coefficients mean in front. So we're being asked to circle subscripts. So any number that is after an element, we could think of subscript like a submarine, right? Submarines go under the water. So the reason why it's called a subscript is it actually goes below the line that we typically write on. So 2 comes after the H. I'm going to draw a circle around it. That's an example of a subscript. Okay. There isn't anything else as a part of H2, so that's an example of a subscript. We have 2HCl, and this time we have the 2 in front of our chemical, so that makes it a coefficient. We have to be able to tell the difference between these because they are each treated a little bit differently when we're counting the total number of atoms in our chemical. And now we've got 4O2. The 4 in front, just like math, anytime we have a number in front called coefficient. And the 2 refers to the oxygen, so that is a subscript. All right, so on to part B. Coefficients and subscripts are different from each other. We're going to list out the elements. So a coefficient is distributed throughout everything. So the 2 in front, for example, would affect the H and the Cl. However, subscripts, that's not the case. Let's list out. We have carbon, C, and we have hydrogen, H. The subscript applies to whatever is directly in front of it, as long as there are no parentheses. Again, thinking in math terms, parentheses means we have to distribute. In this C2H6, I don't have any parentheses. So the number following carbon, 2, my subscript of 2, tells me I have 2 carbons. Hydrogen has its own subscript. There's no coefficient, so I don't have to distribute by multiplying by anything else. So I just read what the subscript is, 6. So I have a total of 2 carbons and 6 hydrogens in that example. All right. Let's go down to NH3. We're going to list out, we have N and H. Now, again, we don't have a coefficient, so I only am going to look at the subscripts. If there's no number written, we know it's 1. So there's 1 nitrogen. But I have a 3 after the hydrogen. So it's only the hydrogen that has the 3 after it. Okay. If we go up to 2 MgO, so coefficient, like in math, gets distributed through the entire chemical. So Mg originally had 1 atom. However, the 2 in front means that I'm going to multiply that by 2, giving me a total of 2 atoms of Mg. Oxygen, or O, originally no subscript, so I have 1. The 2 in front gets distributed throughout, so I multiply by 2 for a total of 2 oxygen atoms. Okay, now let's look at this one right below here, kind of a little bit of everything going on here. We've got a coefficient in front, and we've got a subscript and a set of parentheses. So this set of parentheses, think in math terms, means that the number outside the parentheses applies to what is inside of the parentheses. So in our case, that 3 applies to the oxygen, O, and the hydrogen, H. We also have a coefficient in front. So the coefficient, because there's no parentheses or anything like that, We distribute to every single element. So we have two different numbers influencing my oxygen and two different numbers influencing my hydrogen. Aluminum originally had 1. There's no subscript, there's no parentheses. However, there is a coefficient. So I have to multiply. Okay, I have a total of 3 aluminum. Now, oxygen and hydrogen's work is a little bit different. Oxygen originally has nothing written after it. So I would say normally it had 1. However, the subscript following O after the parentheses means that I'm going to multiply it by 3. I also have to include the fact that the 3 in front is distributed throughout also. So both the subscripts and the coefficients are incorporated, giving us a total of 9 oxygen. Hydrogen originally had 1. The 3 afterwards means that I have 3, and the reason I am including that is it is inside the parentheses. Remember, aluminum was not inside the parentheses, so it did not get multiplied by this subscript. Everything in this chemical, aluminum hydroxide or AlOH3, gets multiplied by the coefficient, so it also still gets multiplied by the coefficient for a total of 9. Okay, so let's look at some examples of balancing chemical equations. We have to balance in order to satisfy the law of conservation of matter, which says every atom that goes in has to come back out again. So if I don't have the same number of atoms on the reactant side as I do on the left side, product side, I won't have a balanced equation. So again, let me clarify since I misspoke. I have to have the same number on the reactant and product side, which means left of the arrow and right of the arrow for each element. So we fill out an atom inventory or an ARP chart. A for atom, R for reactant, P for product. Okay. My first element, P, I have 1 atom on the left, the reactant side. Reactants are to the left of the arrow. And on the product side, I have 4. I can tell that because of the subscript of 4 written after P. Oxygen has, on the reactant side, 2. On the right-hand side, 10. This violates the law of conservation of matter. We make it appear as if I start with 1 and I magically multiply and make 4 appear. Old scientists would have loved this, especially the alchemists trying to turn lead into gold. They would have thought this was great, but sadly, this chemical reaction would not actually happen this way if we didn't have the right number of atoms going in and the right number of atoms coming out. Now, the goal is to get these two equal to each other through multiplication. I can only use whole numbers. If I can think of a way to get them both equal to a whole number in a very straightforward way, that definitely saves me some time. For example, I know that there's a number I can multiply 1 by to get it equal to 4. Sometimes that's not the case. For example, if I have 2 and 3, there's not a whole number that I can multiply 2 by to get it equal to 3. But in this case, I can take the 1 atom of phosphorus, multiply it by 4, and that will give me a total of 4 atoms. It's great to write it in the chart. However, we have to put that as a part of our chemical equation. So wherever I wrote whatever element I wrote that I multiplied by, that's where the number goes. I know that makes very little sense, sorry. So I wrote that I multiplied phosphorus by 4 on the reactant side. I have to put the 4 in front of phosphorus on the reactant side, is what I was trying to say. And 4 equals 4, those are the same. I don't have to necessarily do anything in front of the right-hand side. I might end up having to come back and do that, but for right now, they're equal. This oxygen, now I can think of a number that I can multiply by in order to get my left-hand side equal to 10, which is what the right-hand side already has, and that's 5. And so I would write a 5 in front of the chemical with oxygen on the reactant side. Now, I didn't multiply the products by anything. I just leave the line blank. I didn't multiply it. All right. So let's look at question number 2. Everybody should be able to, at this point, count how many atoms there are in something. That we've done that before. But for Mg on the reactant side, there's 1. Product side, there's 1. Oxygen has 2 and 1. So we can already tell this is not balanced. Therefore, it is breaking the law of conservation of matter. We've got to follow the law. So I'm going to pick one of the elements that's not balanced. Magnesium currently is balanced. I don't want to adjust those. Oxygen, however, I have 2 on the reactant side and 1 on the product side. Now, that gives me a fix. Seems pretty straightforward here. If I multiply oxygen by 2, I do in fact get 2 oxygens. The hiccup comes where I have to write that I multiplied my oxygen by 2 is in front of the entire chemical MgO. It's true, I wanted to double the oxygen. However, I wasn't trying to, but I also doubled my magnesium. For example, if I ordered 2 cheeseburgers, I would not be very happy if they gave me 1 complete cheeseburger and then a bun. Those are not the same things. So because Mg and O come together, I have to get all of that entire chemical. Even if I don't want the rest of the burger, I have to get the whole entire thing if I order a second one. So without intending to, we threw off our magnesium counts. And that's because the coefficient is distributed throughout the entire chemical. Part of the reason we have these lines here is to remind you that's the only place that you can write a number. I can't change the formula by adjusting any subscripts. Otherwise, it makes it into something new. Originally, magnesium was good to go, and we're not good to go anymore. So again, we created a hiccup that wasn't intended. Now we can go fix it. But we know how to do that. We're going to multiply until we get them to be the same number of atoms. So I needed them both equal now to 2, right? 2 is my new goal. So if I multiply 1 times 2, I get 2. I write that in front of the Mg. Now, a question that comes up, why didn't oxygen also get affected on the left-hand side? And that's because they are 2 separate chemicals. So the coefficient only applies to that chemical it's directly in front of. When we have plus or an arrow, we've now restarted. It's not going to be affected by that coefficient. So the final answer for this one has a 2 in front of Mg, nothing, or if you really want to, you could write a 1. Sometimes I know people like to have something in every line. And then a 2 in front of MgO, and that would be a correct, complete, balanced equation that satisfies the law of conservation of matter.